Video, we're going to have a look at what are known as geometric sequences, and then we will solve question 7 on the worksheet. All right, so what's a geometric sequence? Well, it's a sequence of the following form. So I have some initial term, we'll call that A, and then for a geometric sequence, to get from term to term, we just repeatedly multiply by R. Okay, so if I start with A, then multiply by R, that's going to give me the next term, which is AR. Then multiply that by R to get to the next term, AR squared, then AR cubed, so on and so forth. Okay, so this number R is referred to as the common ratio for the geometric sequence. And a slightly different way to phrase this repeated multiplication by R is to say that if I take any two successive terms and divide them, well, I'm always going to get this common ratio, right? AR divided by A, the A's cancel out, and I'm left with R. AR squared divided by AR, well, again, A's cancel out, and R squared divided by R is R. AR cubed divided by AR squared, again, R, so on and so forth. Okay, so here are some examples of geometric sequences for different values of R. So the first example, R is a half, so I have 1, then multiply by a half to get a half, multiply by a half again to get a quarter, then an eighth, 16th, so on and so forth. Okay, the second example, R is -3. Okay, so I start here with -3. And then I'm just going to repeatedly multiply by -3, right? So -3, 9, -27, 81, so on and so forth. Notice the sign change here due to the fact that this multiplier R is negative. All right, the third example, R is equal to 1. Well, there I'm just going to get this constant sequence, 1, 1, 1, 1, 1, right? Because 1 of the n is equal to 1 for all n. All right, the next example, R is -1. And so this is just going to give us 1, -1, 1, -1, so on and so forth. So we're just alternating between these two numbers, 1 and -1. And then lastly, we have the case when R is -0.25. Okay, so my first term here is 1, multiply by -0.25 to get -0.25. Now multiply that value, multiply by -0.25 again to get to positive 0.0625, multiply again to get to -0.015625, so on and so forth. All right, so now before we look at question 7 on the worksheet, looking at these examples, okay, which one of them converge and which one of them diverges? Okay, so let's go through that. For the first example, this certainly converges, right? 1 over 2 to the n goes to 0 because 2 to the n down in the denominator approaches infinity, right? So this is a convergent sequence when R is a half. The next example, this is a divergent sequence. So here you see there's the sign alternation, but also we see that the magnitude of the terms becomes infinitely large. Okay, so in particular, this sequence is not approaching any one specific value, and so the sequence diverges. All right, the third example, when R is 1, well, again, this is just a constant sequence, so it certainly converges and has a limit of 1. For the next example, when R is -1, we actually have seen this example in a previous video. Here, again, we're just alternating between these two values, 1 and -1, but we're not approaching any one single value. Okay, so this is a divergent sequence. And then lastly, when R is -0.25, okay, yes, we have the sign alternation, but here the magnitude of the terms is approaching 0. Okay, so here this is a convergent sequence and its limit is 0. All right, so now let's look at question 7. Well, it's asking for what values of R does the sequence R to the n converge? All right, and so I've just broken things down here in a couple cases. So here we first note that if R, the base here, is a number strictly between -1 and 1, if we raise that to an infinitely large power, so R raised to, say, you know, the 10 billionth power, that's going to give us something infinitely small. Okay, so we saw in the last slide there, right, if R is, say, a half, right, if I raise a half to a very large power, I'm going to get something extremely small, something close to 0. When R was -0.25, again, as we let n increase, right, the magnitude of the terms approaches 0. Okay, so the sequence converges when r is strictly between -1 and 1, and its limit in that case is 0. All right, now in the special case when r is equal to 1, as we already noted, the sequence certainly converges, and its limit in that case is just 1. And then if I am not in between -1 and 1, including just 1, but not -1, okay, then the limit will not exist. Okay, we looked specifically at the case when r was equal to -1, and we saw there was just that alternation between 1 and -1, and we diverged in that case. But if the magnitude of r is more than 1, right, say r is 3 or -5, something like this, raising r to a very large power will give us something in magnitude that's going to become infinitely large, right? The larger that exponent becomes. Okay, so in that case, the limit will not exist, and the sequence diverges. Okay, so we conclude here that this geometric sequence r to the n will converge when the common ratio r is strictly greater than -1 and less than or equal to +1. And I just summarized that on the number line here. So for the various values of r, the stuff in blue there, those are the values for which the sequence converges, and then the stuff in red there is where we diverge. All right, great. That's going to do it for this video. I will see you next time.